I want to take a look at what are called combinations and how to count them. So combinations is a very common word in the English language, but in mathematics it has a very specific meaning. So let's talk about what it means. A combination is a group or collection of items. Okay, the big thing about this is the order of the items does not matter. Okay, so the items could be anything. For example, they could be letters. The collection of the letters A, B, and C is the same thing as the collection of the letters B, A, and C because they're the same group of things. So these are the same combination of things, of items, of letters. Okay, the same combination. Now if you're talking permutations, you would count each of these separately. Okay, combinations are simply a group of things where the order does not matter. You rearrange them, we still consider it to be the same thing. Okay, so let's take a look at an example involving combinations. Okay, so here is an example of a way to count combinations. So we have 24 neighbors attending the annual Homeowners Association meeting. So from those 24, in how many ways could they select 3 people to make up this architectural committee that they're trying to form? So the idea is there are 3 spots that have to be chosen. The order does not matter because in a committee we're not appointing anyone to a certain position in the committee, so we just need a group of 3 people. So order doesn't matter, which tells us we're looking at counting combinations. Okay. Alright, so here's how we think about this. We have 3 people we have to choose. For the first person, we have 24 options. Any of the 24 people could be somebody in the group. The next person we choose can't be the first person, so there are 23 options for who could be second. And last, there are 22 options because we can't choose any of the first 2 people. So it would appear that the answer is 24 times 23 times 22. But there are duplicate combinations here because, for example, let's say we choose person A first, person B second, and person C third. If I stick with this counting scheme, then that means BCA would be counted as a separate combination, and I don't want duplicates. Don't want duplicates. So what we have to do is, sorry about that, what we have to do is get rid of the duplicates. Now for every combination of 3, how many duplicates are there? Well, since there's 3 positions, that means I've got 3 choices for the first position, 2 for the second, and 1 for the third. So that's 3 times 2 times 1. There are 3 factorial duplicates of each option. For example, ABC, I could have ABC, I could have ACB, I could have BAC, I could have BCA, I could have CAB, and I could have CBA. There are 6 different versions of the same group of 3 people, so I need to take 6 and divide by 6 to take it down to 1. So I need to divide by the 6 duplicates I have for every different group of 3. There's 3 factorial duplicates of every option. So ABC is just 3 of the 24. I could have A, B, and D be another one. There's 6 copies of that I need to get rid of as well. So what we need to do is take our 24 times 23 times 22 and divide by the number of duplicates that we have. Okay, so in this case that's 3 factorial. So this is how many combinations or groups of 3 people we could choose to create this architectural committee. I'm calculating that number right now, and it looks like it's 2024. So 2024 ways to create this 3-person architectural committee. Okay, now a couple of other ways of looking at this. You could reason through the entire problem and use this calculation, okay? But I'm going to show you some other ways to think of it. What this is, it's the permutation, right, on top 24 times 23 times 22. That's if the order did matter. So that's the permutations divided by the duplicates. That's how you calculate combinations. All right? So permutations in this particular problem, the way we would write that is from 24 we need to choose 3. So 24p3 for permutations. And we would divide by the number of duplicates, and since there are 3, we're creating a group of 3, there are 3 factorial duplicates of each. And so if you type that into your calculator, you should also get 2024. Okay? So that's another way to think about it. It's the same exact calculation. But finally, the easiest way is we're still doing, so this is still, just like with permutations, this is still 24, choose 3, but the order doesn't matter. So there's 2 ways to calculate 24, choose 3. We've already mentioned one, 24p3, or the new one is 24c3. P is for permutations, and C is for combinations. Okay? This is where order doesn't matter. So we're going to type this into our calculator. There might be a button like NCR that you could use to calculate 24C3, and if you do that you will also get 2024. So this is a very logical way to do it, the way we started with, but what's difficult for people to remember is to divide by the duplicates, because what's on top assumes that the order is important. But we have to get rid of all the duplicates, so we have to divide by the number of those. This method down here, the 24C3, is also very logical as long as you understand the idea of 24 choose 3. From 24 choose 3 distinct items. Okay, so it's very important when you use this concept you have to do distinct items. And in this case, this particular problem, we're choosing 3 different people, 3 distinct people to form the committee. If one person could fill all 3 spots, we could not use this problem solving. Let's look at one more example. So in this example, we're talking about a lottery. We have to pick 6 lottery numbers from the numbers 1 through 45. The order that we choose them does not matter. We're just looking for a collection of 6 numbers. So we're just collect 6 numbers. So the way we could think about this is from 45 distinct items we need to choose 6 distinct items. And because of that, we know we're going to do 45 choose 6. But we know that there's 2 ways to calculate 45 choose 6. There's 45p6 and there's 45c6. Okay? Now, because in this particular problem the order does not make any difference, we just want to collect 6 lottery numbers, we're going to choose this guy because the order doesn't matter. So if you type that into your calculator, let me do that real quick. it looks like we get 8,145,060 ways that we could choose our 6 lottery numbers, okay? So you can see the advantage of this powerful 45C6, or in the case of permutations, 45P6. But if you want to look at it another way, you could think of it as you need to pick 6 lottery numbers. So 1, 2, 3, 4, 5, 6. You've got 45 choices for your first, 44 for your second, 43, 42, 41, and 40 for your sixth. So that's 45 times 44 times 43 times 42 times 41 times 40. But this is all the permutations. This is where the order matters. So we have to divide by the duplicate lottery numbers. Divide by the duplicate lottery numbers. Now since we're choosing 6 numbers, there are 6 factorial duplicates. So divide by duplicate lottery numbers. Okay, so this is more of a reasoned approach to this rather than just using 45C6. And if you type that into your calculator, you should still get 8,145,060 ways. But this is a more reasoned approach, logical approach to it, rather than just remembering to do 45C6. So whichever way you prefer to do it, or whichever way your instructor prefers, maybe be versatile with both of those.